So, a little bit about gases and gas laws. So we have some scientists that you're going to read about. Charles and Guy Lassac came up with the idea, which is now known as Charles's law, that the absolute temperature of a gas is proportional to volume. So absolute temperature, we have to be talking units of Kelvin. So make sure anytime you're dealing with gases, you remember if you're given Celsius temperatures that you convert to Kelvin. And to do that, you just add 273. So Kelvin equals Celsius. 0.15, but a lot of times you're dealing with whole numbers, so you could just go with 273. Boyle and Boyle's law. So pressure is inversely proportional to volume. That's what he came up with. And then Avogadro. And so this is Avogadro. He did not come up with Avogadro's number. That was named in his honor. But what he said was that at the same temperature and pressure, if you have equal volumes, you will have the same number of molecules or the same number of moles. So if you have the same T, P, and V, you're going to have the same number of moles of a gas. It could be, you could be talking about nitrogen and helium, any two gases. We have an ideal gas law, PV equals nRT. You're going to get used to this. R is a universal gas constant. The value is 0.08206 latim per molk, liters, atmospheres per molk. So as far as units, for volume, all right, we've got ideal gas law. For volume, it really doesn't matter what unit you're using. You could be talking milliliters or whatever. But if you're going to use R, an R value that has liters in the constant, then you need this to be liters. For pressure, you could use atmosphere, torr, millimeters of mercury, bar, millibar, kilopascals. So you can use many different units for pressure. However, if you're going to be using an R value that has atmospheres in it, then you need to convert this to atmospheres. So you should get good at converting between units. Now, N is the number of moles of gas that you have, and that has to be in the unit moles, and you can see that that shows up in your R. And then temperature must be in Kelvin. So as far as R is concerned, you need these 4 units. You're always going to need Kelvin for temperature. So if we rearrange this, we say, okay, we have 2 sets of conditions. Conditions 1 could be whatever. Whatever temperature, whatever pressure, whatever number of moles. If we rearrange, we get P1 times V1 over N1 times T1 equals R. If we do the same thing under the second set of conditions, we set it equal to R. We see R is a constant, gas constant. So these 2 things are going to end up being equal. So if you have that, you can actually see Charles's law, you can see Boyle's law, and you can see the relationship that Avogadro discovered. We can just cover up some of these. So for Charles, it was absolute temperature is proportional to volume. And if you cover up the pressure and the number of moles, means we're holding those constant. Right? We hold pressure and number of moles constant. You could see V1 over T1 equals V2 over T2. So if T2 went up, the volume would have to go up proportionally. Boyle's law is that pressure and volume are inversely proportional. So if we cover up the bottom, we see we're holding temperature constant, we're holding the number of moles constant, and if the pressure were to go up, then volume would have to go down to make that statement true. And then the last one is just Avogadro's law, where we're holding everything else constant. We've got 1 over N1 equals 1 over N2. So, well, like we really should have volume in there. We're saying that if we have the same volume, we have the same number of particles. I guess that just looks kind of weird. All right, so that's that part. Kinetic molecular theory. Gases are mostly empty space. So we sort of are ignoring the fact that gas molecules do take up space. If we just assume that it's 0. It's not 0. You can use more complicated calculations, then PV equals nRT, and you can get a little bit better results, but PV equals nRT works pretty good. So we'll take a look at this in a second. Number 2, particles are in constant motion. Collisions of the particles with the container are going to cause pressure. That's where that pressure arises from. 3, collisions between particles are elastic, perfectly elastic. We pretend that when the molecules collide with each other, that they're not sort of like sticking to, they don't have any attractions for each other. They're not being repelled by each other. It's just an elastic collision. And then number 4, the average kinetic energy of gas particles is proportional to Kelvin temperature. So these are some parts of the kinetic molecular theory. So let's look at this one though. Gases are mostly empty space. So I have a 1 liter beaker here, and it's filled with air. And so the question would be, well, how much space in the beaker do the gas molecules actually take up? So if we want to know that, we need to know, first of all, well, how many molecules are actually in here? That's number 1. And then we need to know, well, what's the size of each of the molecules that we're talking about? So I have a 1 liter container, temperature, calling it 25 degrees Celsius, and pressure is about 1 atmosphere. I pretend that I have 3 sig figs, and then we have our R value. So if we solve for N, the number of moles in here, we get 4.089 times 10 to the negative 2 moles of air. I should round that to 3 sig figs, but I'm going to use it again. So we have this many moles of air, and I'm going to now pretend that all this is air is one type of thing. So air's 78% nitrogen, about 21% oxygen, and about 1% argon. Of those, nitrogen is the largest of the molecules, so I'm just going to pretend it's 100% nitrogen. When I look up diameters, I see different values, so I took one of the larger ones that I've seen. So volume of nitrogen molecule, all right, I've got a diameter of 370 picometers, 10 to the negative 12 meters. So volume is going to be 4/3 pi times the radius cubed, and we end up with 2.652 times 10 to the 7th cubic picometers per molecule. I'm going to convert that to cubic centimeters. A cubic centimeter is 1 milliliter, so this has 1,000 milliliters. So I convert that using this conversion factor, and I get 2.652 times 10 to the negative 23rd cubic centimeters per molecule. So I put that down here. I'm going to multiply by Avogadro's number, and I'm also going to multiply by how many moles of air we have. So we convert from cubic centimeters per molecule to cubic centimeters per mole, multiply by the number of moles, and we get 0.653 cubic centimeters. So if 100% of the molecules below this line are nitrogen, they should occupy approximately 0.65 or 2/3 of a milliliter. So, all right, so pretending that it's 0 is, it's not a bad estimate if